Alright, welcome. Today is day 3 of acid and base lectures. It is 5/3, so today is the 3rd of May, 2017. In class today, by the end of class today, you should be able to explain the differences between a strong and weak acid, strong and weak acids and bases, name common binary acids, and oxyacids, which are also known as ternary acids. And that just basically means that it has 3 or more elements in the compounds. We will also be working together in peers, groups of 2 to 4, to calculate pH and pOH, pH, pOH, and acid concentrations based off of given information and some formulas that we will receive today. We should also be able to classify the strength of acids and bases using the pH scale. Alright, so looking at our opening question for today, and I'm going to choose different color ink real quick. Alright, so we have complete these reactions between an acid and a base. First thing, we need to be able to identify which one is the acid, which one is the base. And remember that the acid is the one that's going to donate the proton, or that's going to give away its hydrogen. So HCl is the acid here. Lithium hydroxide is the base. So hydrochloric acid is going to donate a hydrogen to lithium hydroxide. And actually, in this case, it's going to be a double replacement reaction where the hydrogen pushes out the lithium. So in this neutralization reaction, the hydrogen from hydrogen chloride pushes out the lithium, and we end up with H2O, or HOH. The other compound that is formed, now that the lithium is free in ion, it will push out, it will go where the hydrogen once was, and form lithium chloride. Now, one thing to pay attention when you're doing this, remember that this is an ionic compound. So remember that those rules that we learned earlier in the year about forming ionic compounds still apply. Lithium is a +1 based on the fact that it is in group 1A, and chlorine is a -1 based on the fact that it's a halogen, and all of the halogens are -1 charged. In this particular one, we'll crisscross the charges, bringing the one down here and the one down here, and know that those will react together 1 to 1. So we end up with lithium chloride, no subscripts needed. Sometimes you will have to have some subscripts, so just pay attention there. Second one. This one is not as obvious, and it's not technically a neutralization reaction, but we have water plus ammonia reacting together, and one's going to be a base, one's going to be an acid. And remember that water can act as an acid or a base. And so one of the things that we know of is that we know that ammonia is a base. It's technically a Lewis base. And basically, whenever it mixes with water, it produces a hydroxide ion. So what that means is that the water is going to act as the acid in this one. So we end up, that means that water is going to get rid of one of its hydrogens, an H+, and I know that's kind of hard to read because of the color, but it's going to eject one of those hydrogens, so we end up with an OH negative. And this one is actually going to be an equilibrium reaction. It's going to go back and forth. So it's going to be OH negative. And so since we have this free-floating hydrogen ion, where is it going to go? It's going to attach to the ammonia to form a ammonium ion, which is going to be NH4 plus with a positive 1 charge. And goes from there. Alright, so let's go through. I'm going to quickly go through these slides, not spend a whole lot of time on it, but just some reminders about naming acids. And this is only dealing with acids in their naming. So when we're naming acids, remember that if you have something like hydrogen chloride, and it's a binary acid, remember that bi means 2, so we have 2 elements involved in this compound. It's going to be a hydrogen plus another element. So hydrogen sulfide, hydrogen bromide, hydrogen fluoride, anything like that, and even hydrogen and oxygen, which forms water. We can have some things going on there as well. All right, so when we have this situation, we take whatever compound it is. So let's say, for example, we have hydrogen chloride. When we dissolve solid hydrogen chloride in solution into a dissolve it into water, we get hydrochloric acid. So 2 things to note: we take the hydro from hydrogen, and we get rid of the IDE and replace it with IC. So this becomes hydrochloric acid. Same thing, hydrogen fluoride becomes hydrofluoric acid, hydrogen sulfide, hydrosulfuric acid, hydrogen bromide, hydrobromic acid. Now, a change that we see is when we're dealing with ternary acids. Ternary means 3 or more elements, technically 3. So you're going to have hydrogen plus a polyatomic ion.
Jayla Grayson, Marseille Stevenson, Ernest Johnson, come to the front office, please. Jayla Grayson, Marseille Stevenson.
Sorry about that. So we have 3 elements plus a polyatomic ion. Remember, some common polyatomic ions that you might remember would be things like sulfate, it's a negative.
Ryan Munster, please report to the administrative office. Ryan Munster, please report to the administrative office.
So we have things like sulfate, which is a negative 2 charge, nitrate, which is NO3 with a negative 1 charge. You could have carbonate, CO3, negative 2 charge. Several different polyatomic ions. You can look those up. There are charts available all over the place. But basically what we need to remember here is, so we have hydrogen sulfate, which is, let me go ahead. So I'm looking at this one in general. Hydrogen sulfate, the compound is H2SO4. Why is it H2? Again, remember that hydrogen's a +1, sulfate is a -2, so the 2 means that it's going to take 2 of these hydrogens to react with 1 sulfate group, so it's H2SO4. Now, so what we need to know is in these situations, if the polyatomic ion ends in an ATE, ATE becomes IC. So, and we don't worry about the hydrogen being present. Now, in the compound, hydrogen is still there, but we don't use hydrogen in the name. It just simply becomes sulfuric acid. Now, so when you see sulfuric acid, you know that the compound is H2SO4 because it's a sulfate group with hydrogens attached to it. But if we saw hydrosulfuric acid, how is this different? Okay, it's correct. When we see the word
Jayla August, come to the front office, please. Jayla, August.
When we see hydro, that lets us know that it's a binary acid, and so that means it's only going to be two elements involved, so it's going to be HS, or actually H2S, because sulfur is a, if we remember, hydrogen's +1, sulfur is -2, so that means it takes two hydrogens to react with one sulfur. Alright, so that's the distinction there. Whenever you just see sulfuric acid, you don't, the hydrogen is understood. We don't note it any other way. Alright, let's move on. So a different type of polyatomic ion that we get is ones that have the ending ITE. So, similar names. We have, we had nitrate, which was NO3 with a -1 charge, but we can also have nitrite, which is NO2 with a -1 charge. We could also have something like sulfite, phosphite, just to name a few. All right, so let's look at what actually happens here as we're naming these. So we have something like hydrogen nitrate. All right, let me take this one and we'll write it down here. So we have hydrogen, and I'm going to go ahead and go all the way through and form the ion, or form the compound here. Hydrogen and nitrite. Nitrite, we just said, is NO2 with a -1 charge. So when we do our ratio based on the charges, we see that it is HNO2. So we have this compound. Now, the part that we need to know is the only thing that we're going to look at is the actual name of the polyatomic ion that's in there. So we have hydrogen nitrite. If it ends in ITE, it changes to be OUS with acid behind it. So nitrite becomes nitrous. So we get rid of the ite and add OUS. Alright, nitrite becomes nitrous acid, sulfite becomes sulfurous acid, chlorite becomes chlorous acid. Now, the old way that they taught this, and to remember the naming, is basically you look at whatever element is in the center. And so in this case, it is nitrogen in the center, so nitrogen becomes nitrous, and so on. Alright, so just real quick going back, oxyacids that have the ATE ending, if it has an ATE ending, it becomes IC. If it has an ITE ending, it becomes OUS. And remember that binary acids, compound acids with only two elements in the compound, end in IC, and you have hydro whatever element it. All right. So some general information about strength of acids. In this particular one, in HCl, HCl is going to dissociate into a H+ ion and a Cl- ion. In relation for acids, the only thing that's important is the H+, and since there's a 1-to-1 ratio here, it produces 1 mole of H+ ions. 1 mole of hydrogen chloride produces 1 mole of H+ ions. Whereas sulfuric acid, H2SO4, we have 2 hydrogens for every 1 sulfate group. So when it dissociates, it produces 2 moles of hydrogen. So you get a higher concentration, higher acidic property based off of that, because there's a higher amount of moles in this particular compound, moles of hydrogen in this particular compound. All right. Weak acids, what I want you to know here for weak acids is essentially when you're trying to identify something as a strong acid or a weak acid, let me go back a page. All binary acids are strong, meaning they completely dissociate. One exception would be hydrogen fluoride. All right, and going forward, for a weak acid, look for organic compounds. Any organic acid is going to end up being a weak acid. So we're looking for that carbon to be present. And now, the reason why we use the term oxyacids rather than ternary acids is because there are some organic acids tend to have carbon, hydrogen, and oxygen involved in it. So your overall compound is actually going to be more than just 3 elements sometimes. So we just have to kind of pay attention to that. There are some other weak acids, but for right now, all I need you to know is to look for organic acids. Look for that carbon presence in the acid. Strong bases, anything that has a hydroxide in it, an OH in it, so sodium hydroxide, lithium hydroxide, potassium hydroxide, so on. We're looking for that OH, and whenever it dissolves in water to form solution, you'll get sodium ions and hydroxide ions, and the important ion for a base is hydroxide. Moving on. Weak bases only ionize slightly. The main weak base that I want you to know is ammonia, which is NH3. Alright, we're going to skip these slides for today. We will come back to those another time. We are going to talk a little bit about pH scale. Remember that a pH scale is a range from 0 to 14. So we have 0 on one end, we have 14 on the other. Right in the middle, we have 7. 7 is neutral. Neutral, if I could spell. 0 is a strong acid. 14 is a strong base. And then from 0 to, say, 6.9, is going to represent our acids. And then from 7.1 to 14 are our bases. Alright, this is the pH scale. POH scale would be just flipped backwards. POH is just the opposite. So the pH scale is logarithmic, which means each change of a single pH unit signifies a 10-fold change in the concentration of hydrogen. Or another way of saying this, a 10-fold concentration change in the concentration of hydronium. Alright. And as you get closer to neutral, so looking on the acid side, as we get closer to neutral, 6.9 is a very weak acid, whereas 0 is a very strong acid. 7.1 is a very weak base. 14 is a very strong base. In terms of acids and bases, strength of an acid and base are equally dangerous. So very strong bases and very strong acids are equally dangerous in terms of our bodies. So skip that. Let's go to this diagram. This little flowchart diagram, whatever you want to call it, helps us anticipate what calculations we would need to do to make a change from one area when we're given certain information, as far as if we're given information in pH and we need to know pOH. That is actually very easy. If we're given information in pH, let's just say that we had a pH of 4, and we wanted to know what the pOH is. If that's the case, then we can look pH plus pOH equals 14. So if our pH is 4, we can go 14 minus 4 equals our pOH, which equals 10. So our pOH would be a 10. 10 plus 4 is 14. All right, that's an easy switch to go from one to the other. Now, if we are given information as far as we are given the concentration of hydrogen, and we want to solve for pH. pH is equal to the negative log concentration of H plus. Now remember that H plus and hydronium are the same thing, H3O plus. I just use the H plus because it's quicker. Remember that this is a positive as well. So now, if we are given the pH and we want to know the concentration of hydrogen ions, we can go the other way. So we can go, it's going to be equal to the antilog, or second log, of the negative pH. All right. Now, similar situation if we're dealing with pOH. If we want to know the pOH and we're given a concentration of hydroxide, we can find out the pOH by taking the negative log, and it's the same formula, negative log of OH negative. All right, and if we want to solve for the concentration, we take the antilog of the negative pOH. And again, there's always more than one way to get there. So just think about which is going to be the simplest path. Now, this last part, well, let's say that we want to know the pH of something, but we're given in concentration of OH. So we want to know, in order to solve for pH, if we're given concentration in OH, well, we could take this path and get to pH, or we can take this path and get to pH. So when we're dealing with concentration, we have discovered that concentration of hydrogen times the concentration of hydroxide gives us a number of 1 times 10 to the negative 14. And one of the things to recognize about that negative 14 right there is the basis of the 0 to 14 for the pH scale. All right, now, so let's look at it a little bit differently. So we want to know concentration of hydroxide when we're given concentration of hydrogen. So we're going to take 1 times 10 to the negative 14 divided by concentration of hydrogen. All right. If we wanted to know concentration of hydrogen, and just so you recognize, these brackets represent concentration. Same thing. It's going to be 1 times 10 to the negative 14 over OH negative. And we can go one way or the other, and there are, like I said, there are multiple paths to get to the same way. So, all right. So let's go ahead and look at this this little page here and look at it. And I'm telling you right now, the numbers I gave you here are fairly simple. You will be able to recognize a trend, and we can actually kind of cheat and do a shortcut, but you're not always going to be able to cheat and do this shortcut. All right. So we need to identify 4 things. We're given concentration of hydrogen ions. We want to know the pH, the OH, and the POH. So we want to know the pH of it, we want to know the POH of it, we want to know the concentration of hydroxide. We also want to identify this as an acid or a base. We should be able to easily do that when we determine the pH. So if you remember, let me switch to a different color ink. If you remember, to solve for pH when we're given concentration of hydronium, we're going to take negative log of the hydrogen concentration. So I'm going to show you this on the calculator just so that you can kind of see. Move my calculator in a little bit forward. So go on here. It's negative log concentration. So that is 1 second e negative 5. All right. So when we do this, we hit enter, and that gives us our pH is 5. Now, since we have this number, the easiest way to determine POH is going 14 minus pH equals POH. All right, so that's the easiest way. So 14 minus 5 gives us what? All right, so we get a POH of 9. Now, just simply based off of pH, is this an acid or a base? pH of 5 is less than 7, so that means it is an acid. All right, now let's prove some stuff real quick here. All right, we want to know the concentration of OH, the concentration of hydroxide in it. So we need to solve for a concentration of hydroxide, which is OH negative equals the antilog of the negative POH. All right. Antilog is the same thing as saying second log. All right. All we're doing is putting this basically 10 to the power of the negative pH. So pulling up my calculator just to show you how to do this, we are trying to solve for OH negative, so we're going to take second log, and so we get 10 raised to the power of the negative POH, so negative 9 gives us 1 times 10 to the negative 9. Now, what pattern do you notice that's happening with the pH and POH? All right, so yes. So if it has a pH of 5, then it's going to be, the concentration is 1 times 10 to the negative 5. If it has a pOH of 9, the concentration of hydroxide is 1 times 10 to the negative 9. So this one, 1 times 10 to the negative 8, what do you expect the pH to be? 8. 1 times 10 to the negative 0. This one is tricky. 1 times 10 to the negative 0. Anything raised to the power of 0 is 0. So, all right. So, but when so 1 times 10 to the raised to the power of 0 is 1, but we have to actually plug this one in. So just really quickly, just proof of point here. We are really only interested in this number here, so it's going to be 0, but just proof of point is negative log (1) second EE 0 is going to give us a pH of 0. 1 times 10 to the negative 7 is going to give us a pH of 7. All right, so real quick based off of that, if it has a pH of 8, is it an acid or base? Base is correct. If it's a pH of 0, it's an acid or a base? It's an acid. It is actually a strong acid. And if it has a pH of 7, is it an acid or base? It is neither. It is neutral. All right. So quickly going through here, 14 minus 8 gives us 6. 14 minus 0 gives us 14. 14 minus 7 gives us 7. All right. So we could quickly determine that this is pH negative. OH concentration is 1 times 10 to the negative 6, 1 times 10 to the negative 14, 1 times 10 to the negative 7. All right, now I want to come back to this one and just show you another route. All right, we were given the concentration of hydrogen here, and let's just say that we wanted to know this one. So the other route that we could have taken is using our final formula. We could have used that concentration of H plus times OH equals 1 times 10 to the negative 14. All right, so we want to solve for OH. It's going to equal to 1 times 10 to the negative 14 divided by 1 times 10 to the negative 5. All right, so let's see what we get here. So we have 1 times 10 to the negative 14 divided by 1 times 10 to the negative 5. And what should our expected answer be? Should be 1 times 10 to the negative 9. All right, so we should be seeing we should be getting this same answer here whenever I do my calculation. So let's see. 1 times 10 to the negative 9. So there are multiple ways to get to the same point. Just need you to understand that. And I use these numbers because they are simple calculations that we actually didn't even need the calculator to do. Just wanted you to see it as proof of point. All right. So tomorrow we will continue doing pH and pOH calculations. I think you're going to actually like these because they are very straightforward. And if you're given one piece of information, you can determine the rest. And I do promise you that they get more difficult than this number, because you will end up with concentrations like that are, say, 3.5 times 10 to the negative 9. And it's going to not be this. It's not going to be your expected. It's not going to be your expected pH, like we can just predict it based off of that with the 1. So we're going to see it with some different numbers and some different concentrations as we go through. All right, thank you for watching the video. I will post this and tomorrow's lecture. I'm going to post all the lectures this week, so in case you miss, you can